Hi, this is Jeff Heaton. Welcome to Applications of Deep Learning with Washington University. This is the third module of the course. Here we're going to talk about TensorFlow and Keras, just give an introduction into how to use those with the Python code that we've previously been looking at. This is part one, neural network basics. Neural networks have input neurons. What these are able to do is take input from data sets and form predictions. So we're going to look at just a simple feed-forward neural network. Here we might imagine that we have 4 inputs going into the neural network. Consider a very simple neural network, like the iris data set that we had seen the data set for before. It has 4 inputs, which are 4 measures that classify the data into 3 different iris types. So for this, you're going to have essentially 4 inputs going into the neural network. One is going to be the petal width, the petal height, the sepal width, and the sepal height. Never mind what these actually mean as far as measuring an actual iris flower. That's really not what this is about. They're just 4 measures that let you train the neural network to detect what type of flower it is based on those 4 inputs. So this gives you 4 input neurons. Those 4 input neurons are what goes into the neural network. That's your input layer. Because this is a classification neural network, and because there's 3 classes, 3 different types of iris flower, you're going to have 3 output neurons. This would be, I don't know, class 1, class 2, and class 3, because we're classifying. That's your output layer. This area in between are your hidden layers. Hidden layers are what make deep neural networks deep. Previously, before deep learning, we would typically have 1 or maybe 2 hidden layers. Now we can have hundreds. Not all problems require that deep of a neural network, so it's definitely important to consider the problem that you're seeking to solve. So let's look at just the first hidden layer. Just to keep it simple, we're just going to put 2 neurons in that layer. So that's hidden neuron 1, hidden neuron 2. Now each of these layers also have sort of a hidden neuron that you don't really see. It is the bias neuron. So each of those 2 layers has a bias neuron. All of these layers, or all of these neurons, are going to connect to each of the hidden neurons. You're not going to connect to the bias neuron. The bias neuron is output only. So the bias neuron will actually connect to that as well. So this first hidden neuron has 5 inbound connections to it. Then likewise, and they have the same connections to hidden 2. Hidden 2 would have all these same ones. So that first area, weight matrix, between those is going to have a total of 10 weights. Then each of these connects to the next layer. And of course, I won't draw it all the way out because there will be a lot of, oh, by the way, this is class 4. There is no bias neuron on the output layer. Only the input layer and subsequent hidden layers have it. So this is a single layer neural network. Single hidden layer. The calculation that occurs is actually pretty simple. You can think of just one layer, so all of the So if you have just an arbitrary neuron, either its input is going to come from the data set, the P and S width and height over there on the left side of the screen, or it's going to come from the previous layer. So the point is, some input is coming to this, that neuron. If this was a hidden neuron, it would have, let's give it 3. We'll include the bias. And then it would produce some output. If you look at how that is actually calculated, if you want to call this input 1, this input 2, and that the bias, you would think of this calculation as basically being, so that is a weighted sum. You're calculating input 1 times weight 1 plus input 2 times weight 2 plus the bias, which is really a weight between the bias is a single number. It's that line that connects the bias neuron to the next hidden. And then this whole thing gets passed to a activation function. The activation function that we usually use with these type of neural network is the rectified linear unit. Rectified linear unit, we will see more about that. It's a very simple linear input. So if x, and then the output of it is y, if x is anything less than 0, then it's going to be 0. If x is anything greater than that, then y is going to be the same value as x. It's entirely linear at that point. That is essentially what this is doing. It's almost linear regression-like. You're taking a weighted sum of the values, and then we are passing that through an activation function. And this is basically the calculation that gets done for hidden 1, and then hidden 2, and then it gets calculated for the output neuron 1, the output neuron 2, the output neuron 3, and the output neuron 4. So you have to calculate the neural network. It's feed forward because you must calculate from the input forward to the outputs. Your activation functions will be rectified linear unit for hidden. So your activation functions, hidden will always be hidden, and input will be rectified linear unit. Output, it depends. If you're doing output regression, it'll be linear. If you're doing output classification like we're doing here, it will be softmax. And I'll show you the equations for each of those. So now we'll review some of the information that is on the module website. Here you can see I created 2 neural networks, a regression neural network and a classification neural network. The regression neural network, basically these are life insurance-like neural networks. We have, in each of these cases, 6 inputs. We have the insured's age, income, weight, and then some medical statistics about them as well. This is feeding into a single layer neural network. So you've got hidden 1, 2, 3, and hidden 4. And you have a bias on each of the layers, just like I showed you previously. Classification looks very similar. The difference comes in the output layer. We have 4 classes here that we're going to rank the person into: preferred, standard, substandard, and decline. Those are just levels that insurance companies put individuals at to determine what level of premium they're going to have. So neural networks have output neurons. If you have a regression neural network, it's usually going to be just one value. If you have a classification, it's going to be a number of values or output neurons equal to the number of classes that you're expecting. Now, neural networks are very flexible, so you can have multi-regression neural networks where you'll have multiple regression outputs. You can also combine them. You could create a output neuron here that is trained to give you that maximum face amount and do the whole thing all at once. Usually you create more specialized models, but it is possible to combine those two. This is what a neural network looks like if there are two hidden layers. The individual structure that you want to think about that I was showing you from the time before is you have one neuron that's being fed by multiple, in this case 3, parent neurons, or input values if they're coming from the outside. So those 3 inputs are essentially just a weighted sum. It's all a bunch of weighted sums as you feed forward through it. You can't calculate the weighted sums for hidden layer 2 because you haven't calculated layer 1. So you essentially move through, you put the values in for input 1, input 2, and you move forward through the neural network to make those calculations, eventually culminating in the output neurons, and then you're done with that. Later we'll see that when we train it, there is a back propagation technique, and that back propagates the errors backwards through it. So it's feed forward, back propagation. Back propagation is what adjusts these weights so that the neural network learns and can produce meaningful output. We have input neurons, hidden neurons, output neurons. Later we'll see there's context neurons. When we get into LSTMs and recurrent neural networks, there are bias neurons. Every layer except for the output layer usually has a bias neuron. This is very similar to the y-intercept in linear regression. So this is the neural network calculation that I showed you a little bit on the freeform drawing pad earlier. Basically, what the neural network is going to calculate is a function of its input. So this is the calculation of a single neuron, not the whole neural network. It's a calculation of this that you see below. So it is essentially calculating, the function is the activation function, whatever it happens to be. Sigma is calculating the sum. And we are essentially calculating the sum of all of the weights over I by the inputs. Now, the bias neuron is treated like an input. Often it's input 0. So what we do to cause that to happen is the bias would have a weight, but we would append a fake 1 onto the end of the input just to account for the bias neuron so that he essentially gets summed. Here we have input 1, 2, 3. The way you would think of the weight, the bias happening, maybe input 3 becomes the bias. You would always put a 1 in for that input, but it would still have a weight. Weight 3 would become the bias, and it would simply get summed because you're multiplying 1 by the bias, which anything times 1 is itself. Then we pass it to the activation function, and we finally get our output. So this is showing you what the bias calculation would look like. You're passing in 1 and 2, but you append a 1 onto the end of it so that you get a coefficient of 1 that basically causes the bias here, which is just the third weight, to simply be added to it. So to do the calculation, you're going to multiply your weight of 0.1 times 1, because that's what it corresponds to. 0.2, your second weight, corresponds to the second input, so that gets multiplied by 2. And then your bias would be 0.3, which that is actually a typo. That should be 1. So to calculate that actual summation, you take the first input, 0.1, I'm sorry, the first input is 1 times its weight, which is 0.1, plus 2 times 0.2, plus the bias, which is 0.3, times that 1 coefficient that you put in, which effectively causes the bias to simply be added to it. This is very much like the y-intercept. And then the whole thing is passed to the activation function. Like I showed you earlier, we have 3 activation functions that we deal with. There's actually quite a few activation functions for neural networks. However, it's mostly converged to using the rectified linear unit, the softmax, and the linear. The rectified linear unit is essentially just a, like I said, it's going to be it's the maximum of 0 and x. So it's essentially linear greater than 0, or 0 when it's less than 0. The softmax, all that the softmax does is takes those multiple outputs. So if you had 3 classes, it ensures that those output neurons sum to 1. It effectively makes them probabilities. There's a web application that I created that you can play with for softmax just to illustrate it. So say we had 4 classes. Those neurons are going to output a variety of values. You can't really control what the neurons are going to output. They might be very large, they might be fairly small. This fairly large outputs from the neural network would mean that usually it's the highest output wins. So if there were 4 classes, 1, 2, 3, 4, this neural network would be specifying class 3, which is 10. But these values, you don't want to just take the highest neuron output as the class. You would like to have probabilities. And you can calculate the probabilities by doing that. You can see that in this case, this 10 is so large that the probability for the third input, which is J2, because it starts at 0, is 0.99. And these others are pretty unlikely. So this basically takes the output from the neural network, which won't always be, which will rarely add up to 1, and crunches it into probabilities. You always use softmax, or at least you usually do, with the output of a classification neural network. And that's just showing you how you do the calculation for that. If the output neurons are for a regression, then you're going to use a linear function, which simply is the same value. So whatever the output neuron is, that's going to be the regression value. Rectified linear unit has become the primary activation function used with neural networks. Previously, the sigmoid-shaped activation functions were common. You might have heard of sigmoid and hyperbolic tangent. This is the graph of a sigmoid function. It was used primarily as a squashing function. So if your x is near 0, your y is also going to be, but it very much squashes the values to between 0 and 1. Hyperbolic tangent looks very similar to this. They're both S-shaped. It's just the hyperbolic tangent function, 0 is more where the middle of the S is, and it squashes between -1 and 1. The way that we train these neural networks is by looking at derivatives. So the derivative is the instantaneous rate of change. So if you look at just one weight all by itself, so this is multivariate calculus, you're taking partial derivatives. So you're taking the derivative of one weight, the error of one weight. So how far away is the output from the neural network away from what you want it to be? How big is your error, which is y on this, for each of these weights? So as you increase the weight, the error of the neural network increases and then decreases sharply and then starts to increase. If you had infinite computation time, you would just calculate this graph for every single weight on the neural network, and you would just pick the lowest value. But you don't have infinite computation time. That would be a lot of computing to do because these numbers are very dense. There's a lot of decimal places in between them. What scale, what granularity would you loop across? So it's very difficult to do that. But if you take the derivative, you can get the slope of this error function at that point. And you can see from that slope, that blue line is the derivative, that it's starting to point downward. This slope that you have here would be a negative slope. So you need to add to the weight. You always flip the sign of the slope to know what to do to the weight. If you want to go in this direction and you've got a negatively sloped gradient, you have to add to the weight. So you'll usually see that negative sign in the update rule that basically flips that around and causes you to descend. That's why this is called gradient descent. We're trying to descend to a lower error value. The reason we use rectified linear unit is because of the way the derivative looks for this. So for the derivative of the sigmoid, it basically squashes to 0 as we get further away. This leads to something called the vanishing gradient problem, where all of your gradients go to 0. And if your gradient goes to 0, you can't really make any adjustments to the weights anymore because you have no slope on this line that was just above. And then why are bias neurons needed? Bias neurons do the same thing as the intercept. So this is a graph that shows you the y output from a neural network as we adjust a weight. So as you adjust the weight, you're somewhat changing the slope of the sigmoidal output from the neural network. If you make it negative enough, you can scrunch it out to pretty much a linear relationship, or you can make it more S-shaped. As you adjust the bias, you tend to shift the entire value across the sigmoid-shaped output from the neural network. So bias shifts, whereas weight changes the slope. And this is just for one neuron. There's a whole bunch of neurons contributing to the output from this. Okay, this is the end of part 1 for this module. In the next part, we will take a look at TensorFlow and start to see how we can actually construct some of these neural networks in code.